All right, so we're going to start our lecture into the chemistry, the chemical composition of the body. And this is basically how the basic function of the body, how we keep things homeostatic and how the body functions is through chemistry. So we got to use this. I know it's kind of one of those scary topics for most of you that haven't had chemistry, but we'll get through it and we will teach you basically the nuts and bolts, kind of baby chemistry. It's just the chemistry that we're going to use for the body. We're not going over a whole semester of chemistry. I'm trying to keep it as a functional chemistry that you're going to need to understand the physiological processes. So when we looked at the level of organization of an organisms, we saw the smallest level being the atomic level, made up of atoms. If we put multiple atoms together, we make molecules, and then multiple molecules we can make cells, and multiple cells we can make tissue, and then further up to the organism. But as I said, with physiology, we're going to focus more on this atomic, molecular, and cellular level. So let's first look at atoms, since molecules are basically made up of bonding of different atoms together. So let's look at what makes an atom. And if you probably all have seen the periodic table before, these are the different atoms in the world. And we will look at what makes up all of these atoms. Have this key feature. They all have a nucleus, and that nucleus shown here, the central nucleus, is made up of various amounts of protons and neutrons. Protons having a positive charge, and neutrons are neutral, not having a charge. Okay, so the nucleus here, made up of protons and neutrons, has a positive charge to it. Surrounding the nucleus, floating in, basically not in these circles, but if you can think of it as a spherical cloud around these around the nucleus, are these electrons, these smaller electrons. These electrons have a negative charge. Okay. So we have a positive nucleus made up of protons and neutrons, and these outer clouds or shells holding these negative electrons floating around it. Okay. And what differs between, say, hydrogen here and helium is the amount of protons and electrons in each of these atoms. Okay. One number we'll focus on here, and you see on the periodic table, you see number 1 for hydrogen, number 2 for helium, 3 for lithium. Here is, this is the atomic number, and the atomic number correlates to the number of protons that are in the nucleus. Okay, so therefore for hydrogen with an atomic number of 1, it contains 1 proton. Helium, on the other hand, with an atomic number of 2, would have 2 protons in it. Okay. The other key feature of these atoms are they are electrically neutral. Okay, they are neutral in charge. Therefore, if you have, say, a positive 1 for each proton and a negative 1 for an electron, there needs to be an equal amount of protons equal to the amount of electrons for each atom. Therefore, our friend hydrogen, it contains 1 proton in the nucleus, and therefore it has, to make it electrically neutral, it has 1 electron floating around it. Okay, it would just have 1 of these and 1 proton. Where helium would have 2 protons, okay, in the nucleus, and to make it electrically neutral, it would have 2 electrons. Okay, this is going to become important because the amount of electrons are what determines how reactive these different atoms are. So now let's look at how these electrons are arranged in these atoms. Okay. And you remember the periods are as we go across in rows, and the groups are in columns here. But these electrons, you see, remember hydrogen. Hydrogen has atomic number 1, so it has 1 proton, and therefore if it's to be electrically neutral, it has to have 1 electron. Okay, so these electrons, they aren't haphazard. They sit in these shells, and these shells can hold various numbers of electrons to be filled. Okay, there are S shells, and you can see the purple here. You can see 1, 2, 1s. So an S shell holds 2 electrons, and it is filled. Okay. Atoms like to have their electrons filled. That makes them stable. Stable molecules have their shells completely filled. There is another shell, a P shell, that holds 1, 2, 3, 4, 5, 6 electrons. So if an atom has all 6 electrons in the shell, it would be stable. You can see the ones that have their filled shells are lined up in this group here. These are the noble gases. Okay, they're stable. They don't have to gain electrons to become stable. They already have their shells filled, so they have stable. Okay. There's also a D shell that holds 10 electrons. You can see 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And this would be stable. So these electrons fill in this increasing order. They fill up as 1s. So 1, 2. All right, once that's filled, you got 2s. Looking here, 1, 2. Now that's filled. The 2p, remember p holds 6 electrons. So 1, 2, 3, 4, 5, 6. Okay. So you can see this gives the different atoms their chemical reactivity. If you want to think of it, you can think of all these atoms here want to become like the noble gases, because these atoms are filled. They have their electron shells filled, so therefore they are stable. So elements are trying to become very similar to this, with their electrons. Okay, so let's take a look at, say, carbon. We're carbon-based life forms. We'll see why carbon is such an important element and why it's versatile, because let's look at the electron configuration. So carbon sits here. It has 1, 2, right? And then we have to fill the 2s, so 3, 4. And then it sits here, 1, 2. So it has 2 electrons in this 2p. How can we get, what would we have to do electron-wise to get carbon to have the same amount of electrons as the noble gas here, neon? We would have to add 1, 2, 3, 4 electrons to the carbon shell. Okay, we're looking here. We'd have to add 1, 2, 3, 4, and we would have filled the S and the 2p here. Okay, and that would give carbon a stable configuration. Right? Again, the atoms, they want to have their electron shells filled and want to be similar to here. So for carbon, we would need to add 4 electrons to its shell to get it to have its 2p filled. Let's look at, say, sodium here. Sodium's on the other end of the spectrum here. We're over on this side of the groups, looking on this side. Okay, sodium. What's easier for sodium? Do you think it's easier for sodium to do? Add 1, 2, 3, 4, 5, 6, 7 electrons to become like argon? Or would it be easier for sodium to lose 1 electron and then it has a similar configuration to neon, which is stable? Again, it's stable gas. Yeah, it would be easier for sodium to lose an electron, come here, than to add 7 and become like argon. So the group of elements here, when they are reactive, they react and tend to lose their electrons or share their electron more readily. Where molecules over here, or sorry, not molecules, atoms over here tend to want to gain electrons. You can see an atom like chloride. What's chloride need to do? Chloride just has to gain 1 electron and then it has its 3p shell filled. Okay, so if you want to think, this is simplified chemistry, but if you want to think, how many electrons does a molecule need? You can think they all want to become similar to the noble gases, and which is the easiest way? Okay, is to either lose or gain. The one kind of caveat is hydrogen. Okay, remember the elements over here, even though hydrogen only needs to gain to get helium, it's easier for hydrogen to lose its electron, okay, or to give it away, or to share it more readily. Okay, so that is kind of one of the difference. It'll lose the electron here rather than gain one. Okay, but elements over here tend to want to readily share or give away their electrons, where elements over here want to gain. Okay, so let's take a look at the next slide. So the amount of electrons determines kind of the reactivity of these atoms, and specifically the outer electrons, okay, determined. So something like lithium. Lithium has hydrogen, or sorry, 1 electron, 2 electron. So this shell is filled, but then it has 1 electron from the 2s shell. Okay. And so we will see that if you want to think of it, that these atoms want to be similar electron-wise to these neon gases here. These are stable gases because what do they have? They have that p shell completely filled, so they are stable. Okay, so if you want to, you can think of it as all these atoms want to become similar electron-wise because to these noble gases, because these noble gases have their p shells filled. They are stable. Okay, so something like lithium. Lithium, how could it get similar to one of these noble gases? Okay, one way would be to add 1, 2, 3, 4, 5, 6, 7 electrons to it, and it could be like neon. But wouldn't it be easier for lithium to lose an electron and be similar electron-wise to helium. Yeah, so atoms on this side of the periodic table tend to want to lose or give away their electrons. Whereas when we come to this side of the periodic table, okay, one molecule carbon would have to gain 1, 2, 3, 4 electrons. So if it gained 4 electrons, it would be like neon. Okay. Or let's look at another atom we'll be seeing quite extensively is chloride. For chloride to become similar to this noble gas, chiefly would be argon, it just needs to gain 1 electron. So chloride really wants an electron. All it needs is 1 more, right? You get so close to something, you want it even more and more. So chloride, to get here, needs to have just 1 electron, and it can be similar electron-wise to argon. It can have its shell filled. Okay, so molecules that want to have electrons are considered more electronegative. These atoms over here want to give away electrons, where atoms closer to here want to really take electrons. So there is a term called electronegativity. And as you move across the periodic table from left to right, the electronegativity increases. So very low electronegativity, none to very low, to very high electronegativity over here. Okay. So how do these atoms, how do they get to be similar to these noble gases? How do they get electrons? And to gain electrons or lose electrons, the atoms do bonding. Bonding with other atoms is how they can fill these shells and become similar to neon or argon. Okay, so what we're going to be doing is doing bonding to basically become similar to this. So chiefly the amount of electrons in those outer shells determines on how reactive a molecule is. Where these atoms on this side, they want to gain electrons, and atoms on this side want to lose. Helium is kind of the oddball because it can gain an electron and it's filled, or it can also lose an electron. So it's kind of one of the funkier ones. But most of these atoms want to either gain an electron, so they are similar electron-wise to these noble gases. Let's look at one other common one we'll be seeing a lot of, sodium. Sodium's on this side, right? It has shell filled here, and all this shell's filled here, and then it just has 1 electron sitting in this 3s shell. So how can it get similar to the noble gas? Yeah, if it gave away an electron, it would be similar electron-wise to neon. Okay, so these sides typically want to give away electrons. This side, the highly electronegative side, wants to gain an electron. Okay. Alright, so a way for these non-noble or stable elements like carbon, nitrogen, oxygen, these all elements need to gain electrons to become similar to these noble gases, or elements over here have to lose electrons. So to get this stable configuration electron-wise, these atoms can form bonds with other atoms. And there are cases where they can share electrons, they can take electrons, and so forth. So sharing of electrons comes in the form of what we call covalent bonds. Okay? This is where atoms will share electrons. Okay? Let's look at O2. So oxygen sits here. Okay? And here is what O2 would look like. It's two oxygen molecules bonded together and covalently. Covalently means they are sharing the electrons. One's not taking one from the other. They are sharing the electrons. But for oxygen, how many electrons does an oxygen atom need to gain to become similar to neon here, at least electron-wise? How many electrons does it need to fill this shell? 2. So oxygen is going to share 2 electrons with another oxygen molecule. So you can see this oxygen atom is sharing 2 electrons with this oxygen atom, and this oxygen atom is sharing its 2 electrons with vice versa. So now these oxygen atoms are essentially half-filled shells, so they are stable since they are sharing those electrons, which allows it to fill out those shells. Okay, so this is what's taking place in bonds. In covalent bonds, it is sharing of the electrons. Okay, we can also, in this case, this is sharing of 2 electrons. So this would be considered a double bond. Okay, if you look at, say, nitrogen up here, how many electrons does nitrogen need to fill out the shell? It needs 1, 2, 3. So nitrogen N2, nitrogen gas, is 2 nitrogens bonded together. And in this case, how many would they need to share? They would have to share not just 2, but 3 electrons. So you can get a triple bond. Okay. How about a single bond? Hydrogen. Hydrogen needs to gain what? 1 electron to, right? Comes similar to helium. How about oxygen? Oxygen needs to gain 2. So what if it shared 1 electron with 1 hydrogen and another electron with another hydrogen? So therefore, hydrogen would have 2, and oxygen would have 8, and this hydrogen would have 2. Okay, but what are you seeing here different compared to, say, this configuration with electrons? In the water molecule, where are the electron between these bonds? Where are the electrons closer towards? Which atom? You can see they are pulled closer to the oxygen. So this goes back to that electronegativity. These molecules over here are highly electronegative. So when they form bonds with, say, hydrogen over here, hydrogen wants to kind of give away its electrons, where oxygen wants it's electronegative. It wants to hold tightly. It's gimme, gimme, gimme electrons. Remember, electronegative. I want to hold those electrons tightly. So when these bonds form, the electrons are pulled closer to the oxygen. They are not shared equally. Whereas both of these oxygen wants these electrons equally, and they are equally shared. In a covalent bond, when the electrons are equally shared, you can see, makes a non-polar bond. There are no negative or positive pulls to the molecule because the electrons are held basically equally close to each of the atoms. Whereas with polar, where are the electrons? The electrons are pulled closer to oxygen here. And therefore, they are not equally shared. Remember, oxygen, when it only has 6 electrons, it is electrically neutral. Now it essentially has almost 8 because it's not equally sharing these electrons. There is a negative pull to the molecule. And hydrogen, since its electron is not equally shared and it's pulled closer to oxygen, there is it's not a charge, but it's a positive pull to that molecule. So this would yield a polar molecule. Okay, these are key terms to know. There's big difference between nonpolar and polar molecules. Okay, because we see these guys, these different molecules tend to not play with each other. Nonpolar likes nonpolar, polar likes polar. Okay. So polar molecule, the electrons are not shared equally. So there's a negative pull to the molecule and a positive pull to the molecule. Okay, where nonpolar molecules, there is equal sharing. So there is not this negative, there's no negative and positive pull here since they are equally shared. So we know that now covalent bonds are sharing electrons, so these atoms can share electrons to become similar electron-wise to these noble gases, and that is covalent bonding. Let's look at one specific atom, carbon. Okay, we are carbon life forms, and let's look at why this atom is highly important. Because think of these molecules. We are forming molecules and we are bonding to these other atoms. What's unique about carbon? Let's look at oxygen first. How many electrons does oxygen need? How many bonds does it need to make to get its shell filled? Yeah, it has to share 2 electrons. Okay, so it can make 2 bonds. It can make a bond like we saw with water to 2 hydrogens. Okay, but what's unique about carbon? How many electrons does carbon need to fill this outer shell? Right? It needs 4 more electrons. 1, 2, 3, 4. So therefore, carbon can form bonds with 4 different atoms. So it can make 4 bonds. This makes it unique and makes it so it can be very diverse in the groups or the molecules that can be formed with carbon, because you can have different molecules, different bondings forming off of carbon. It can form 4 bonds, where oxygen can only make 2 bonds. So we can get a diverse amount of molecules because we have all these bondings, these 4 bonds that can be made with each carbon atom. Okay, so this carbon atom can be bound to another carbon, and that carbon can be bound to 3 other atoms. So you can see we can make these very diverse molecules by making these 4 bonds with carbon. And we'll see that in a bit when we start looking at the organic molecules we'll be dealing with. So some more terminology you might come across is terminology called hydrophobic and hydrophilic. We've already looked at molecules that are polar versus non-polar molecules. If you remember, the polar molecule, kind of like water, has, or as you see glucose here, there is a positive pole and a negative pole to this molecule. Here's the positive pole and the negative pole, and there's not, can be multiple poles on here, but that gives the charge. The electrons are not shared equally here. That gives that oxygen a more negative charge over here and a more positive charge over here, since the electron will be found that's shared by the hydrogen, and oxygen will be pulled closer to the oxygen. Okay? And so this gives this molecule a polar characteristic, right? A difference, a separation of charge. And the a polar molecule would be hydrophilic. Okay, hydrophilic is water loving. Okay, remember, water is a polar molecule because there is a negative charge at the oxygen and a more positive charge at the two hydrogens. Okay, so hydrophilic. This shows you that polar molecules like other polar molecules. Okay, so polar molecules will readily dissolve, not readily, but will dissolve easier in water, because we are going to be talking about solutions in a bit, and our solutions in our body, our solvent is water. So polar molecules can dissolve easier in water because they are water loving, hydrophilic. The opposite end, hydrophobic molecules. If you remember, non-polar molecules. If the electrons between the covalently bonded molecules are equally shared, for the most part, they are considered non-polar. The classic non-polar molecule you'll be seeing throughout the semester is, if you look here, we haven't gone over the whole nomenclature, but each of these points is considered a carbon molecule. I'll have a handout on different nomenclature to show you how the different bonding is taking place in the molecules. You can see up here they use a line, but this here is considered, each of these is a carbon. Okay, each point, one here, one here, one here. So long chains of carbon, even if they're associated with, say, an oxygen molecule at the end here, they are typically, the charge is equal across this molecule. So they are non-polar, and non-polar molecules are considered hydrophobic, okay, water fearing. So non-polar molecules don't mix well with water. Where polar molecules, our hydrophilic molecules and polar ones will mix well with water. Hydrophobic or non-polar molecules will not. They're less soluble. So these large, if you ever see these large carbon chains, you can tell the characteristic of the molecule is hydrophobic or non-polar. Yeah. All right, so let's look at some other bonding that can take place. Covalent bonds are sharing atoms, sharing electrons between atoms. And this, we'll see the covalent bond is a very strong bond. Okay, it's a high energy bond. It is very strong. But we can also get what's called ionic bonding. And I apologize for having the periodic table on everything here, but to explain this is when I wish we were definitely in class at this point for this chemistry lecture. But let's look at this ionic bonding. Okay. This is between molecules on this side of the periodic table with molecules over here on this side of the periodic table. Because remember, these molecules are highly electronegative, this fluoride and chloride. Okay, because what do they need? They just need one electron to fill the shell. So they want an electron badly. They want them badly. where these molecules over here, what do they want to do? They're not electronegative. They're the opposite of this. They want to they're readily willing to give away their electrons so they can become similar to here, where sodium wants to give away an electron so it can be similar to neon here, electron-wise. Okay, so chlorine wants an electron badly. Sodium's readily willing to give it away. All right, and so sodium and chloride will form what's called an ionic bond. In this case, instead of sharing the electron, okay, chloride takes the electron. But remember chloride. Chloride as an atom is electrically neutral because it has equal amount of protons and equal amount of electrons. But what happens if chloride takes an electron from sodium? Now chloride has one more electron than it does have protons, and therefore it will gain a negative charge when it takes this electron. How about sodium? Sodium had equal amount. It had 11 protons and 11 electrons, so it was electrically neutral. But when it loses its electron to chloride, what's going to happen with sodium? Sodium's going to only now have 10 electrons and 11 protons, so it will have a positive charge. Okay, this forms what we call ions. Okay, when sodium loses that electron and becomes positive, it is a cation, forming a positive ion. And you'll see it written as sodium with the little plus subscript. And chloride, when it steals an electron, all right, it becomes a negative ion and is an anion. Okay, and it will have that chloride with the negative superscript there. Okay, so these form negative ions. Okay, so there's a positive charge and a negative charge, and this attraction between positive and negative forms this ionic bond. But this is a weaker bond than the covalent bond. Okay, covalent bonds strongest, ionic bonds are strong but definitely weaker than covalent bonds. Okay. And we'll see since these ionic bonds are weaker and these ions are positive and negatively charged, when you put these ionically bonded molecules, they dissolve or dissociate in water. Because water, remember the sharing of electrons between hydrogen and oxygen is not equal. So there is a negative pull here and a positive pull to the water molecules at the hydrogen. So when you put these sodium chloride ions in water, sodium chloride in water, the positive hydrogen side attracts to the chloride, the negative chloride, and the negative oxygen side attracts to the positive sodium ion and separates that ionic bond. And basically we get what's formed, these hydration sphere. So when you put ionically bonded molecules in water, they dissolve or dissociate in that water. The last of the bonds we're going to go over here is, we've already looked at covalent. Those are sharing electrons between the atoms. Ionic is where one atom basically takes the electron and the other loses it, and then there's a shared attraction between each other, which is our ionic bonds, and then our hydrogen bonds. Hydrogen bonds are weak attraction between hydrogen and an electronegative molecule. You see, a common hydrogen bond is between water. Remember water. Here's our oxygen, our big red. Remember, the shared electrons between hydrogen and oxygen are pulled more closely towards the oxygen. So this gives the oxygen molecule a negative pull. Since the electron's being pulled away from hydrogen and is not shared equally, it's less shared with the hydrogen. Therefore, this hydrogen portion of the molecule has a positive pull. Okay? And in water, we got millions and millions of water molecules. How they line up is that negative pull of one molecule is attracted to the positive pull of another molecule. Okay, so this is what we're going to see in hydrogen bonding. Hydrogen bonding is when hydrogen is basically bounded to more electronegative, typically oxygen and nitrogen. Okay, not so much with carbon, but oxygen, nitrogen. These are more electronegative, and they aren't going to equally share the electrons with hydrogen. Okay, you can see other hydrogen bondings. Here's that water. You'll see it written as dots, or you can see it written as slashes. You'll see these little dashes here are the hydrogen bond. Okay, that positive side of this water molecule is hydrogen bonded with the negative pole of this water molecule. Okay. Another common molecule with hydrogen bonds that you guys are probably pretty aware of is this is a strand of DNA here. And you see this is one strand and DNA is two-stranded. Here's the second strand. Those two strands are bound together with these hydrogen bonds you see in the middle here. Okay, this is the weakest of bonds. Okay, so if we look at strength of bonds, we got covalent at the top. It's the strongest, then ionic, and then we go hydrogen bonding. Also, before we move on, we can look at a distinction between different molecules that are formed, different compounds. We can have inorganic or organic compounds. The difference, inorganic, okay, usually last carbon. You can see down here, there are molecules with carbon that are considered inorganic, but they are less complex molecules. Here we just have one carbon for each of these molecules. Okay. Also, inorganic can be ionic, like sodium chloride, okay, or covalent, like you see in water. Okay. Water is considered inorganic. Salts, bases, acids, we'll get into these in a bit. Common acid you see is this carbonic acid, which we will be talking about quite prevalently throughout the semester, and the bicarbonate, which is a base. Okay, these two we'll be talking about fairly regularly throughout the semester. Okay, but the difference between inorganic, organic compounds contain carbon. They are more complex. Usually there are lots of carbons bound to carbon, bound to carbon, bound to carbon. There are multiple carbons bound to each other, usually, and they are always covalent, whereas inorganic can be ionic or covalent. Okay. We need to make this distinction because we're going to be talking about various organic compounds, such as proteins, carbohydrates, and nucleic acids. We're going to look at the structure of these molecules in a bit here. So now let's talk about solutions. If you remember from the previous lecture, we talked about the different fluid compartments of the body. We had the extracellular fluid that included the plasma and the interstitial fluid, and then we have the intracellular fluid, the ICF. So these are all solutions. Solutions are basically a solvent. The solvent is what dissolves the substance, which in case is a solute. Okay, and the solute is what is dissolved in the solvent. Okay, common solution that you guys are probably pretty aware of is saline. And that's simply that ionic compound, that NaCl. Remember, ionic compounds dissociate, so that sodium will become a cation, and that chloride will become an anion. Negative charge chloride, positive charge sodium ion. Okay, but this sodium chloride dissolved in water is saline. And for our case, our solvent, since we're talking about the body, our solvent is going to be water, H2O. Okay, so we have these fluid compartments, and basically it comprises of different amounts of solutes and different kinds of solutes in water. We do need to learn what concentration is. Okay, I'm not gonna ever make you in lecture calculate out a concentration, but what I need you to recognize is what concentration means. Okay, you will see concentration labeled as 1 molar or molarity. Okay, this big M. All right, that is molarity. That is a unit for concentration. And basically, concentration is telling you how much of a solute is in a solution. When we look at our atoms, if we have 1 mole of atoms, could be any atoms. 1 mole, though, comprises of 6.02 times 10 to the 23 molecules, or sorry, not molecules, number of atoms. Okay. If you put that many molecules, 1 mole, into 1 liter, okay, 1 divided, so 1 mole over 1 liter equals 1 molar concentration. What if you took twice as many molecules of, say, hydrogen? You would have 2 moles then. So 2 moles divided by 1 liter, that would give you 2 molar. So basically what that molarity is telling you how many particles are dissolved in a solution. What I need you guys to recognize is the difference between 2 molar and 1 molar. Okay, 2 molar has twice as many particles, so there are much more solutes. It is higher concentration. 2 molar is twice as much concentration as a 1 molar solution. Okay, so this is, I don't like to bring math into the equation here because it just, a lot of people are mathematically inclined, but I need you to understand the concept of what we'll be comparing. We're going to be comparing different molarity, and we're going to add another layer to this when we add osmolarity. But what you need to know is what that molarity stands for. It stands for how many solutes, atoms are in the solution, or how many solute molecules, depending on what you're looking at. Okay? So molarity is telling you concentration, how much of what substance is dissolved. Okay, and 1 molar solution would have this amount of atoms or molecules in it. 2 molar would have twice as much. A 3 molar solution would have 3 times as much. In, again, you got to keep this at 1 liter. Okay, so that is what molarity is telling you, how much solute is actually dissolved. Okay, because we're going to be taking and looking and comparing the solutes between, say, outside the cell and inside the cell. So you need to understand this concept of what concentration means. So since we're not in an actual lecture hall. We won't have you discuss in groups, but you should be able to understand the concepts here of what solution is least concentrated. Okay, some may have the same concentration. So we do have to take into account the difference between this is 1 molar and this little m would be a millimolar. Okay, if you think milli, there are 1,000 millimolars in 1 mole solution. Okay. So I will post something showing you how to look at, but if there's 1,000 in 1 molar, 500 millimolars would only be half a molar. So you can see how these solutions could be equal. Okay, typically we're going to be dealing with this with a milli, since we're using small volumes. It's, we're looking at a cellular level, so typically we'll be hanging out in the millimolar, and again I'm going to add a layer with the milliosmolarity. Okay, but just recognize, look at this, if you were to look at these two concentrations, which one would be less concentrated than the other? Okay, that's a concept you need to recognize. You need to be able to recognize the difference between which one is higher and which one is lower concentration between these two solutions. Alright, so let's get to the crux of this, because this is what we'll be looking at through most of the semester, is chemical reactions, because this is how your body operates, is typically through chemical reactions. This is how we get energy. This is how we get things done and functioning in the cell, is by doing millions to billions to trillion chemical reactions throughout the day. And so let's look at what's taking place in this chemical reaction. We have C, carbon, and as you see H4, carbon is bound to 4 hydrogen. So this is one molecule here. Okay, then we have 2 molecules of O2. So oxygen bound to another oxygen molecule. Okay, so this is kind of the terminology you got to look at, and the scripting. I'll again post something chemistry to give you an idea and show you the different ways some of these molecules will be written out with the different nomenclature, whether, because you could also write this as C. Okay. This C4 is basically this. Carbon bound to each of these is a bond bound to 4 hydrogen. This is what the C4 is. Okay. And then oxygen, that's oxygen. And if you remember, oxygen wants to form double bonds. We saw that in our molecules. That is O2. So we have 2 molecules of this and 1 of this. Okay. This would be our reactant side, because our equation's going in this direction. Okay. So the CH4 plus 2 molecules of oxygen, the reaction takes place and we end up with CO2, carbon dioxide, plus 2 molecules of H2O, water. So what is essentially taking place in here? Let's first count in our chemical reactions, let's count our carbons on each side and our hydrogens on each side and our oxygens on each side. Okay, so carbon, we have on this side 1 carbon. On this side we have 1 carbon. Okay, how about hydrogen? We have 4. Okay. We have 4 hydrogen. over here we have 2 molecules of H2O, and each molecule of H2O has 2 hydrogen. So again, we have 4 hydrogen. How about oxygen on this side? We have 2 molecules of O2, so 2 times 2, that's 4 molecules of oxygen. And what do we have over here? We have 2, and we have 2 times 1. So we have the same amount of carbons, hydrogen, and oxygens. So we haven't lost anything. Okay? We haven't lost any atoms. But what is the difference? The difference between this side and this side are the bonds that are made. Basically, in a chemical reaction, we are rearranging the bonds between the different atoms. Okay, we have the same amount of atoms. Instead of carbon being bound to hydrogen, we have carbon. See, carbon bound to hydrogen here. We have carbon bound to 2 molecules of oxygen. Okay, so that is essentially what is taking place in chemical reactions. Bonds are broken, and then new bonds are formed. Okay. There is energy in this. You got to realize, moving forward, if you remember these bonds are formed. In this case, we got covalent bonds. There is energy in these bonds. We have to put energy in to break these bonds. Okay, remember, these molecules are highly attracted to each other. So to break the bonds, we actually got to put energy in to break them. But then once they're broken, we can form new bonds. So that is all that essentially is taking place in the chemical reaction, is we're rearranging the bonds. So chemical reactions, we saw the first one, we saw the arrows going in this direction, but we will see that many chemical reactions are reversible. Okay, the reactants here can be formed into the products here, but these can also be the reactants and form the product there. So we will talk about, there are some factors that affect which way this reaction will take place. And so we'll discuss that in a bit, but just bear in mind that these chemical reactions can take place in both directions in most cases. And we will see with many of our chemical reactions, there are enzymes that are involved to speed up the reaction. If recall that in chemical reactions, we're breaking bonds and reforming new bonds. Okay? And many times there is energy that needs to be put in. All reactions need energy to be put in because, again, we are breaking bonds. So we have to put energy in. Sometimes that energy is quite great, right? And these chemical reactions won't take place unless that energy is met. So that is the function of the enzymes. And we're going to spend a good chapter, a good lecture on enzymes. But basically the function of the enzymes is to speed up and catalyze these reactions that normally wouldn't just naturally take place. Okay? And when we see, you'll see reactions, you'll see the reactants with the products and the arrow going towards the product. Above or below the arrow, you will see the name of the enzyme that is basically called catalyzing the reaction. Okay? The only thing is these enzymes don't become any part of the product. Okay? They're simply there to catalyze this reaction. They don't add any atoms or anything from the reactants to the product. They're there to speed up, and we are going to talk in great detail about the actions of these molecules, these enzymes, because they are important in making all the chemical reactions in our body take place. Okay, many of your genes, you probably heard the word genes, are codes to make these different enzymes that catalyze the reactions in the body. So most of you probably have heard of acid and bases and maybe heard of pH. pH is just the measure of almost an acid, basically the measure of what we call hydrogen ions. Okay, so if we took water and looked at the water, we had pure water in a vase, we would not find solely H2O. H2O does ionize to hydrogen ions and hydroxide ions. Okay, remember, ions are negative charge and positive charge. That's a cation. This is the anion. Okay, not a large amount. Most of it will be water, but a very small amount of the water molecules will ionize to hydrogen ions and hydroxide ions. Okay, I'm going to make a point of this now because you may hear me call this as hydrogen ion, or also called a proton. Because if you remember, hydrogen is the nucleus consists of one proton and then there is one electron. Since this is a positive ion, this hydrogen atom has lost an electron. So essentially, what is left here? Only a proton. So you can hear this as hydrogen ion, or proton is another common term for it. You'll probably hear me, typically I'll be using proton, but essentially that is a hydrogen ion. Okay, like I said, there is a small amount of this, small amount of H2O that ionizes. It's 10 to the negative 7th. So 0.00000001 molar is ionized to hydrogen ion and hydroxide ion. So what is an acid and a base? If we were to put an acid in water, acids are molecules that can release a proton or hydrogen ion. Okay. If you look at our common acid, hydrochloric acid, this is a hydrogen ion, ionically bonded, because remember this chloride is highly electronegative. If we put this hydrochloric acid in water, remember what happens with ionically bonded molecules? They dissociate. So this would become, down here, we put this in water, all of this would become hydrogen ion and a chloride ion. So what this molecule here is defined as an acid, because when we put it in water, what does it add to the solution? It adds hydrogen ions. Okay, so acids can release hydrogen ions. Okay. Another common one's phosphoric acid. The one we're going to see throughout the semester is going to be carbonic acid. Now, carbonic acid is covalently bonded. Okay. Whereas we saw this is ionically bonded, so all of this hydrochloric acid will, when put in water, will become this and the chloride ion. So all of the hydrochloric acid will donate, each molecule of hydrochloric acid will donate a proton. Okay, Carbonic acid is covalently bonded. So when you put this in water, some will be formed, will dissociate into this hydrogen ion, and this is bicarbonate, HCO2 negative. Sorry, HCO3 negative. Okay, so this would dissociate into this and this, but not all of this will dissociate into this or this, whereas hydrochloric acid, all of it will dissociate into forming hydrogen ions. Okay, that basically gives you whether it's a weak or strong acid. Okay, hydrochloric acid would be a strong acid because all of these hydrochloric acid donate a proton, hydrogen ion, whereas carbonic acid is considered weak acid since only a small or certain amount will donate. Much of carbonic acid will stay as carbonic acid. Okay, it will not all dissociate into this as we see with hydrochloric acid. Okay, but both of these are acids because they do donate or release a proton. The opposite end is a base, a molecule that combines with hydrogen, okay, or can ionize to produce a hydroxy ion, because if you have lots of these hydroxide ions, right, they will combine with this to form water. Okay. You can see our bases here. Sodium hydroxide. Again, this is ionically bonded, so all of this will become sodium and hydroxide. So we will have lots of hydroxide ions in this solution if we put sodium hydroxide in water. Okay, so that would make it a strong base. It's a base because of this, right? A base donates or releases hydroxide ions. Ammonium hydroxide, similar to our carbonic acid, is covalently bonded, so not all of this becomes this, but a certain amount will become this. So it does donate or release hydroxide, therefore making it a base, but not all of this releases hydroxide ions, and therefore it is a weak base. Now, what is pH? Okay, pH is going to be the measure of protons in a solution. Okay, so let's take a look. All right, so measurement of the hydrogen ion. Okay, that proton is basically called pH. But you can see, okay, what's going to add hydrogen ions to a solution is going to be acids. What would remove or make this number smaller would be bases. Okay, but look at the equation for measuring the measurement of pH is log of 1 divided by the concentration. So when you see these brackets here, that means concentration. Okay, so higher concentration would be attributed to acids. Lower concentrations would be attributed to bases because they remove those hydrogen ions. They bind to hydrogen ions in a solution, so they would remove them. So if this number was bigger, which would be for an acid, and since it is in the denominator, then the actual number would be lower. When a solution is acidic, the P, even though the concentration of hydrogen ions is more, because we measure pH is 1 over the concentration, so it's the denominator. So when this number goes higher, then the pH goes lower. Okay, the logarithm just means that each change in number in pH means a tenfold either decrease or increase in these hydrogen ions. But the key here is that increased hydrogen ions brings pH lower. As we continually increase pH, as we continually increase hydrogen ions in the solution, our pH goes down. Bases would make this number lower, and therefore if you divide 1 by a lower number, it would actually be an increase. So bases, if you put a base in a solution, the pH is going to be higher. Okay? Water, if you remember, water ionizes at 10 to the negative 7. Right? If you put that concentration in here, 10 to the negative 7th, and did the calculations, you would come up with a pH of 7. Okay. Anything on the pH scale, anything above 7 would be considered basic, or you also will hear the word alkaline. You've seen those waters in the market. They're like at 9, pH of 9, so they're in this alkaline or more basic than water. Whereas acids would be contribute to a solution that is lower than pure water at 7. Why is this important? Is your blood pH. Your blood pH is one of those homeostatic values. Your blood pH hangs around 7.4. Okay, but remember, homeostasis is not a set point, so usually around 7.35, between there and 7.45. Okay, within that range. You start getting farther and farther out over this range or under this range, your body's going to have, you get too low and your body's going to start shutting down. The cells cannot operate and you start getting organ failure. Okay, this is one of the tightly, we'll see there are multiple regulations for keeping blood pH within this range here. Okay, it is very important that blood pH keeps within this range and doesn't get too far out of here. So as I said, your blood pH stays within that range. Okay, anything below 7.35 would be considered acidosis. Anything above in your blood pH considered alkalosis. So you can see, where does blood pH fall on the scale? Yeah, blood pH on the pH scale, blood pH is more alkaline. All right, it is greater than 7. It's not below 7. If it was below 7, it would be more acidic. Okay, so we keep this relatively constant. Okay, some instances, what might change? Where might we get some changes in blood pH? What would excessive vomiting? From your anatomy days, if you remember, vomiting will be vomiting up stuff that's in your stomach. And what else did you see was in your stomach? Your stomach is acidic. Okay, your stomach is acidic, so it has lots of protons. Okay, if you continually vomit, okay, you're going to be getting rid of these, and you actually have to replace the acidity in the stomach, and you do that through pulling these. Ultimately, this would lower the level of these in the blood. So what would happen if you lowered this level? Your blood pH would go more in the alkaline direction. Okay. We'll talk about bicarbonate, carbonic acid buffers are here to counteract that. That is what this equation is up here. Pulling this out here because we will be talking about this throughout the semester. Okay, this is carbonic acid and this is bicarbonate. All right, you have relatively high levels of this in the blood and levels of this in the blood, higher amounts of this, but you have, your body keeps this in your blood because it's going to help buffer, and buffer by we mean buffer the pH, prevents this pH from going wild extremes, going up, down. It helps buffer the pH in a nice range. That's what we're going to talk about here in the next slide. All right, so now let's look at how one of the ways in which pH is buffered. pH is kept in that homeostatic range. And to do that, your blood has what we call a buffer. Okay? In this case, the buffer is bicarbonate. Okay, HC3O3, this is bicarbonate. You might want to write that down. This is bicarbonate. Okay, H2CO3, this is carbonic acid. If you remember when we looked at the acid, this is a weak acid. And weak acids, some of it disassociates into this, but not all of it. A lot of it still stays as carbonic acid, but a small amount will disassociate into bicarbonate and will release the proton. Therefore, it's an acid. Okay, but if you keep, basically a buffer is a solution with lots of weak acid and lots of, this would be a weak base. Okay. So, law of mass action. So a chemical reaction, you can see this chemical reaction can go in both directions. And there can be changes that take place that cause this to go one way or the other, the rate of reaction. So if I was to take pure water and I dropped in some carbonic acid, let's just say 4 out of the 5 molecules, we'll just use 5, stayed as carbonic acid, but 1 would disassociate into this, into bicarbonate, and into proton. Okay, so not all of it is disassociating. And this would happen, it would go back and forth until we reach what's called equilibrium. There's an equilibrium for these equations. And that means the equations go in the same rate back and forth. But we can change this rate by, one of the factors we can change is adding more. Okay, adding more to one side. So this equation, if you can think, once we reach equilibrium, okay, we've put a certain amount of carbonic acid in. We've gone back and forth. We've got in our 4 carbonic acids, so our 1 bicarbonate and proton, and our teeter-totter now. Okay, here's the carbonic acid side, and here's the bicarbonate side with the proton. Okay, we've reached equilibrium. But, so this will show us how we buffer out our protons here. Okay, because we want to keep this level of this within a certain range because that keeps our pH within a certain range. We got drastic changes of this, either lower or higher, it changes our pH. And we need to keep that pH in that homeostatic range. All right, so what if, when you guys work out, if you work out super vigorously, you make lactic acid. Lactic acid gets released into the blood. And what do you think an acid's going to do to your blood? Yeah, it's going to add this to your blood. Okay, you don't want these levels to get super high. So you want to, if you could draw the equation this way, then this would bind to the bicarbonate and come carbonic acid. If this is bound in carbonic acid, it is not a free proton anymore, and therefore that doesn't alter the pH, because remember, pH is a measure of this, okay, of a proton. So that is what you can look it up, Le Chatelier's or law of mass actions. So we've reached equilibrium, we're here, but now we've worked out and we've added protons. So we've made this side of the teeter-totter heavier, right? And so we've added weight to this side because we've added protons to the solution. How can we draw the teeter-totter back to level? Okay, and that's what happens when you add from one side here, one of the reactants, it will push the equation in this direction. The rate of reaction will be greater in this direction. And when the rate of reaction is greater this way, that means these protons are being bound to bicarbonate and becoming carbonic acid. They are not free protons anymore. So that is what is happening with law of mass action, or look at Le Chatelier's. We've added protons now, but now we've pushed in this direction and we've had those protons that were here bound to bicarbonate, and we've made bound to bicarbonate and become carbonic acid. So now we've made the carbonic acid side heavier, and we've lost some of the weight here by binding those up, and now we're back to equilibrium. So that is essentially how the buffer solution is working. If you have high amounts of this, okay, the changes in this determines on which way the rate of reaction, right? If this side, if we say we ate a bunch of Tums, Tums are antacids, so they're going to remove protons, and they can remove protons from the blood. So if you remove this, now the side becomes lighter. Okay, even though you remove this side becomes heavier compared to this side because you're removing this part of the equilibrium out. So now it would be the opposite. This would be here, and this would be up here if we remove the protons. Now how would we get our equilibrium back? Yeah, our carbonic acid, the rate of reaction can be pushed this way, and therefore we're taking away weight from this side and putting it on to this side, okay, to make it back to equilibrium. Okay, so that is how a buffer system is working. You keep high amounts of a weak acid and high amounts of a weak base, and so the changes in this determines which way the equal rate of reaction is going to be. Okay, and that allows us to buffer out changes in this carbonic acid. Okay, this is just an example I kind of used on the previous slide, is removal of gastric acid. If you remove gastric acid, you're going to decrease this in the blood. So this number is going to become lower. If this number is lower, then our teeter-totter is going to end up in this direction. All right? Because the weight's lower here, this weight, ultimately, if this is lower, gets lowered here, the weight here is heavier. So which way will we need to push the weight to get the teeter-totter back up? Yeah, our carbonic acid can replenish, go in this direction. Now this side's getting lighter, and we're pushing this direction, and this side is getting heavier. So that will help bring this up, or bring this down, and this side up. So our equation gets pushed in that direction. All right, and that's how buffers are operating to maintain that pH, maintain that level of protons in the blood. So I know that concept of buffering and stuff, it gets a little, it's those that haven't had chemistry, it's a kind of complex thing. So I will post some stuff up, some internet resources and so forth to help you out. I'll also go over in Zoom. I will make sure I make a point so I definitely don't want you to get hung up on this, because we need to get you on the level with this, because we will see that equation, that carbonic and bicarbonate equation, quite readily throughout the semester. But let's move on. We're going to look at organic molecules. If you remember, organic molecules, they have carbon. Okay, they have carbon in them, and they are typically more complex. And if you remember, what was unique about carbon was carbon. This is carbon here, is it can bond to make four bonds. So we can make these very diverse molecules because carbon can bond to four different things and make four different bonds. Okay, you can see there are differences here. You can see organic, we got carbon, carbon. All right, there's our 1, 2, 3, 4 bonds. This carbon has 1, 2, 3, 4 bonds. Okay. We can have carbon with just 4 hydrogen in it. And what's happening here? Again, we still have 4 bonds, but this molecule and this molecule, even though they only have 2 carbons, have different characteristics. Okay. This is 1, 2, 3, 4. Again, each carbon has 4 bonds, but in this case, instead of binding to 3 hydrogen, each carbon, we have a double bond between the carbon. So you can see these small changes in these bonding give a difference in ethylene is different than ethylene, chemically wise. Okay, and will react differently. So let's look at the diversity in the bonding that can take place in carbon. You can see over here, hexane, cyclohexane, benzene, they all are a 6-carbon molecule. Okay, they all have 6 carbons. Right? The difference is the amount of hydrogen and the bonding that's taking place. So all these 6-carbon molecules have very different properties, different boiling points, different freezing points, and so forth, and have different uses in, say, the industry. Some are used in varnishes, some are used as cleaning agents, and so forth. So this is just small difference in chemistry. Here we go from hexane, which is basically a linear molecule, to cyclohexane, and then the difference, which is a cyclic compound, and then cyclohexane to benzene. What's the difference between these two? Is there is just double bonding. This gives it what's called aromatic. Okay, and this gives it different properties. So these different small differences in chemistry make a big difference in the way these molecules react and the properties of them. But you can see the diversity that carbon has, because it can bind to four different atoms, gives it the ability to make very diverse molecules. So carbon isn't bound to carbon and hydrogen only. That's not the only molecules or atoms that carbon will bind to. You can see we can get different functional groups by carbon's binding to different atoms. Okay, and you do need to know some of this chemistry, because we will be seeing this throughout the semester. But a carbonyl group. A carbonyl molecule has carbon with a double bond to oxygen. Okay, a hydroxyl group is OH, carbon bound to OH. This is the functional group. Carbonyl group, hydroxyl group, the OH. Some of you this is found in a common molecule you guys might drink. Those of you that are over 21, this is what makes a molecule in alcohol. Sulfhydryl, that's sulfur, hydrogen bound to carbon. Amino, okay, nitrogen with 2 hydrogens. This we will see in a molecule that we will be talking about pretty regularly. You eat it in your diet. Anybody know? Amino acids. Yes, amino acids have this functional group in them. Carboxyl group. This is another one. So amino, carboxyl, hydroxyl, these are ones, probably the three important ones, and then also phosphate. We won't see sulfhydryl or carbonyl as much. Okay? But actually, sulfhydryl we won't see that much, but carbonyl we'll also see when we see ketones. Okay? Carboxyl, carbon bound to double bonded to oxygen and a hydroxyl group. This carboxyl group makes organic acids. Okay, organic acids have this functional group because this hydrogen, what's the definition of an acid is it can release protons. So this hydrogen can get released. And then another one we will be seeing quite prevalently is a phosphate group. Okay, here's the functional group for phosphate. Okay, you will see a molecule ATP. Okay, adenosine triphosphate. Okay. This tri means it has three of these groups bound. Okay. So these give us different kind of molecules, and we'll see here these different functional groups will yield us to different molecules. Okay. Once we've seen okay, ketone. We will see ketone throughout the semester. That has a carbonyl, right? Organic acids, you can see has that carboxyl group. I'll go back to amino acids. Amino acids, you can see we have an amine group. We saw that NH2, that functional group, the amino functional group. And your amino acids will also have a carboxyl functional group to it, okay, making it an amino acid. And then your alcohols have your hydroxyl group here, your OH off the carbon. So like I said, that carboxyl group produces organic acid. Common one, those that work out, you've heard of lactic acid, or you don't have to work out, but your muscles, when you work out heavily, produces lactic acid. You can see it has a carboxyl group. And lactate, we release that proton. That makes it an acid, right? Because it will release the proton. Okay? And I know I won't be, you guys are last semester talking chemistry. I don't understand I will use lactic acid. I will never give you this structure and tell you to tell me what acid or what compound this is. Okay, that's for a biochemistry class. What I need you to know is the functionality, what makes this an acid, and that's a carboxyl group. And if it is an acid, what's that allow it to do? It will release a proton. Okay, but you will see these throughout the semester, but on a test, I'm not going to have you guys you may have to recognize a functional group per se, like you saw on those previous slides, but I'm not going to give you a compound with ... or I could give you a compound and say, hey, what functional groups are here? And you would say a carboxyl group, or also a hydroxyl group. Okay, so that's a fair question, but I'm not going to tell you, hey, what is this actual molecule, per se, by just giving you the structure. So, but you need to know why these functional groups, and because we will be seeing and using these throughout the semester. Some other chemistry terminology, just because it relates to health, and you all have probably heard some of this in the news, but okay, a molecule can have basically the same chemical structure, and if I was in class, I'd give you the 3D structure of this so you can see the difference. But you see this in a two-dimensional plane. In a three-dimensional plane, you can take this molecule, even though you can see it has all the same structure, they're not the same. They actually have this difference. Here, with this double bond, the carbon's on the same side, where they are opposite of each other in the trans. So this is cis and this is trans butane. You guys have probably heard this in the news health-wise you haven't really heard the news cis, but you probably have heard the term trans fatty acids, trans fats. Don't eat trans fat. And that's good information because typically your fats that are found in nature have a cis conformation. You'll see fatty acids, we will see those in a bit, have these long chains of carbon. Okay, and if there's a double bond in it, which side the carbons are on compared to the, okay, it would be this long chain of carbon. Okay, and depending on what side the hydrogens are, the staggered, or if they're on the same side, gives it the cis or trans conformation. Okay. Your body, cis, is the fatty acids that are found in nature. Okay. Typically, trans are hydrogenated; they're produced for the most part. Okay, there are some that exist, but typically in nature, fats exist typically in cis conformation. Your liver knows how to deal with these. Your liver has a harder time dealing with high amounts of trans fatty acid, and therefore the detrimental health effects of these trans fatty acids. You get high bad cholesterol, the LDL cholesterol and so forth, and high fatty acids because your liver has a hard time dealing with trans versus cis. And kind of the main point here is these small changes in chemical makeup and just one way it's bonded determines how it can have a drastic effect on health. So in class this works a little bit better since you don't have your notes to go back, or you gotta talk with somebody in your class about it. I kind of have you, but if these are good questions to look at, see if you understand them. In the Zoom meeting I can go over and we can go over some of the answers, but this is good information for you. All right, so let's start looking at some of the common organic molecules we'll see throughout the semester. Most of you probably know this molecule, carbohydrates. Most of you might know the common one, the sugar, table sugar, or glucose. Okay, and you can see this each individual carbohydrate molecule is a monosaccharide. Okay, we can bond two carbons or two carbohydrates together and we can get a disaccharide. And then if we bonded more than two, we would get a polysaccharide. Okay, but what is common between these molecules is the chemical equation. Okay, carbon, the general formula is you have a certain number of carbons. Okay, in this case for glucose, galactose, fructose, you have 6 carbons. Any carbohydrates, they will have double the amount of hydrogen per carbon that they have, and each carbon will have an equal amount of oxygen. Therefore, carbo, and this is H2O, carbohydrate. Okay, and that's the general formula. So if you had 8 carbons, you would have 16 hydrogen and 8 oxygen for the carbohydrate. Okay, but that is the structure. And you can see again, there is just small differences. Look at the difference. These all have galactose, fructose, glucose all have the same chemical
equation. 6 carbons, 12 hydrogens, 6 oxygen. Okay, it just depends on where the oxygen, here the oxygen's OH is here. It differs from this where the OH is here. Because you got to remember these are three-dimensional molecules, so that small differences changes characteristic or changes the molecule. In that case, it's galactose and not glucose. So as I said, if you have two carbohydrates bound to each other, you have this would be a disaccharide. This would be lactose. This is galactose plus glucose bound to each other. Now we have a string of two carbohydrates. We have a disaccharide called lactose. Okay, two glucose together gives you maltose, so forth. Okay, so those are disaccharides. You can continue and you can bind multiple carbohydrates together in a chain and you get polysaccharides. Okay. And I want to point out how these are formed. I don't like to harp on the chemistry, but we need to know the chemical reaction, the type of what's happening. You can see glucose, right? We're going to put these two together, right? And let's look what happens. From one glucose, we're going to bind this O to here. You can see this O becomes that O there. So now we have a bond between this glucose and this glucose. And what gets formed? Okay, what is here? Two H's and an O. We form H2O. Okay, when you dehydrate something, what do? You take water out of it. So we're dehydrating, or if you condense, condensation. So this condensation and dehydration reactions, when we're binding these two together, we're forming the bond, but we're also forming water. We're dehydrating, or condensation. Okay, these are dehydration condensation reactions because we are forming water. Sorry about the markup on this. I've done this slide twice and it won't erase off. But formation of di and polysaccharides, you have to go in. For this slide, this is the same diagram you'll see on the breakdown of these polysaccharides, but let's form. So we got to go in this direction. We're going from this molecules to here. We're taking two disaccharides and forming a polysaccharide chain. And how do we do that? We bind these together and we form water. Okay, so we're doing a dehydration or a condensation reaction. Those are the same. Okay, and I'm going over this because we perform these reactions are performed to create many of our large biological molecules in the body. Our proteins are made up of amino acids. So binding amino acids together, we get dehydration, making the long strands of DNA. We are doing dehydration reaction between nucleotides, okay, and forming water. Okay. So that's why I'm pointing this out. We do need to know, we don't need to know all kinds of reactions, but we do need to recognize this dehydration condensation reaction. Okay. So let's go in the reverse order. Now we want to break down carbohydrates, or we want to break down, we're going to see our proteins. Now we're going in this direction. We're taking starch. Okay. Starch is basically a long chain of glucose. You can find it in your bread. You got this big polysaccharide. We got this polysaccharide, add in water, and we can add the water to this bond, and we break it. So this kind of reaction is called hydrolysis. Hydro, because we're adding water, and we're lysing this large chain. So now we're taking the polysaccharide and breaking it down into 2 disaccharides. Okay? And ultimately, when we're doing digestion, we're going to take the disaccharide and hydrolysis and break it down to each monosaccharide. Okay? So we will be doing these reactions with both proteins, nucleic acids, because we're going to look at these 2 large biological molecules, and we're also going to be doing condensation reactions to form them, hydrolysis reaction to break them down. So on my previous slide, I forgot to mention probably one of the more popular ones of our biological molecules, lipids or triglycerides. Okay, our fats. Okay, our fats, our triglycerides, are made up of this glycerol backbone. Okay, and 3 fatty acids. Okay, an acid. What's an organic acid have? It has a carboxyl group. Okay, this is a long chain of carbon. Okay, long chains of carbons. If you remember what are long chains of carbon, what is their characteristic wise? Are they polar or non-polar? Yeah, even though there's an oxygen here, this long chain of carbon with hydrogen, okay, equals out the charge throughout this molecule, making this a non-polar molecule. So I'm bringing this up because we're going to be seeing this terminology, and this is going to come into play pretty soon when we start going over membrane transport and so forth. So these are the kind of parts of the chemistry, the nuts and bolt chemistry that you guys are going to need throughout the semester. As I will say on Zoom, if you're having trouble, I know this is one of the sticking points for most people. If you're having trouble, come see me, and I want to help you guys out to get this under wraps so you understand it clearly. But again, going back to the triglycerides, we got a glycerol backbone. We're going to bind our fatty acids to this glycerol backbone. Okay? And that gives us this, but what do we yield? Again, what kind of reaction are we performing? Yeah, we're performing a condensation, dehydration reaction when we bind the fatty acids to the glycerol backbone. So what do we do if we want to use the fatty acids, we want to break the triglycerides apart to use the fatty acids for energy. So how we break down our fat, we need to do a hydrolysis reaction. Okay? But this is our lipids, our triglycerides. So some terminologies on our fatty acids. You guys have heard in the news probably, you've heard the difference between saturated and unsaturated fatty acids or fats. This is a saturated fat. Okay, what do you see with these carbons? What's the difference between this and the unsaturated? Unsaturated omega-6, or you probably heard fish oils, omega-3 fatty acids. Those are unsaturated. The saturated, all these carbons besides this N carbon are bound to hydrogen only. Okay, unsaturated fats have double bonds, so this carbon isn't bound to 2 hydrogens, okay, because of that double bond. And you can see 3-dimensional wise, okay, there's a quirk in these where this saturated fats will lay flatter. These have kinks in them, and so the saturated fats can basically, since they're flatter, can be right next to each other. So if you've cooked bacon, what happens after you cool it off? It gets all congealed because these fatty acids can basically stack on each other and make it a more solid form. Where, like olive oil, you see it at room temperature, what does it look like? It's not this greasy, fat that you see in the bacon after it cools down. It is in liquid form because these fatty acids can't be stacked together because of these kinks in them. Okay, and this has health implications too. Okay, saturated, typically you want to limit the saturated, and unsaturated are typically going to be the good fats for you. But again, just small changes in chemical bonds in the molecule makes a big health effect, a big difference in the chemistry in the body. So here is that terminology we saw earlier, that cis and trans. Here's our cis, hydrogens on the same side. It gives us kink. Okay, more like a slight V shaped, whereas this trans, okay, the hydrogens are on opposite poles when we look at that double bond. Okay, and if you remember, this has a health effect. Your liver is good at dealing with these cis fats. These trans fats, though, okay, your liver has a hard time processing them, and you end up with high amounts of LDL and decrease in HDL. We'll see later in the semester LDL is that bad. Okay. Cholesterol. HDL is the good cholesterol. Okay. So again, small differences in chemistry make a big difference in the body. Another molecule you've probably heard readily in the news, ketones. Already heard of ketogenic diet. That's when you eat lots of fat. When you eat lots of fat, you keep your blood sugars low. Okay. Your body needs energy. It needs a constant, your cells of your body need a constant supply of energy. So if the blood sugar is low, we got to figure out a source. And so when you eat ketogenic, since the blood sugars are low, your body starts utilizing that fat, starts releasing lots of fatty acids into the bloodstream to be used as energy. When this takes place, when you have lots of amounts of fatty acid, when the amounts of fatty acid in the blood are high greater than what you're actually using, your liver will take those fatty acids and convert them to ketones. One of those is acetic acid. Okay, again, why is it an acid? It is got a carboxyl functional group on it. Okay, but this is one of the ketones. Your body will break down, and so your Atkins diet or your ketogenic diet, you get rapid breakdown of fat. So what do you think will happen to your blood pH in this case? Typically, you're not producing lots of ketones, but now with that rapid lipid breakdown, you got lots of fatty acids and you're making ketones, which are organic acids. So this can be released in the blood. So if you have more of this in the blood, your blood will become slightly more acidic. Okay? That's called ketoacidosis. That differs than acidosis. This typically doesn't get to pathological levels. We'll see a case in which we get acidosis and it can become pathological. But on a ketogenic diet, your blood pH will go down a bit, but it won't be out of that 7.35 range where we want to keep our pH. And want to make note of one special type of lipid. Remember, our lipid has this glycerol backbone. Okay, a phospholipid is a triglyceride, and we have a fatty acid, and then here is fatty acid. It has a phosphate group. This is a phosphate group. So we got the glycerol, and we have a phosphate group off of one of the carbons of the glycerol. This gives it a polar characteristic. Okay. But if you remember these long chains of carbon that make up our fatty acids are nonpolar. So in this molecule, we actually have two different things going on. Amphiphatic. Okay, we have a polar end. They call it the polar head of the molecule. Remember, polar is hydrophilic. It loves water. Where we have the nonpolar fatty acid chains that are hydrophobic. Okay. So nonpolar, polar. Doesn't like water, likes water. We are going to see this because this makes up that cell membrane you talked about in anatomy when you talked about the cell. Phospholipids make up this cell membrane. Okay, so we'll see that later in a little bit, especially when we go to membrane transport.
Another type of molecule we'll be seeing fairly regularly is steroids. Okay, not like other lipids, they're not these long carbon chains, but they have these rings, and these rings are very stable and nonpolar, so they are small nonpolar molecules. Okay, so keep that in mind. Nonpolar cholesterol is nonpolar, but cholesterol also, many of your hormones that we were talking about are derived from cholesterol. You can see cholesterol here. This is a structure. You can see just small modifications to this here give us cortisol, your stress hormone, a little more modification, testosterone, and then estradiol, all those hormones. So they are all steroid and they are non-polar. Okay? So non-polar or hydrophobic, meaning fearing water. Okay? So now the functional molecules, the ones that do a lot of the functioning in the body, are your proteins. Okay? And everybody's heard DNA, genes. Okay. Genes are basically codes to putting our proteins together. So, you know how important DNA is, so you can imagine how important these proteins are. We have all that DNA, and basically that DNA are codes to put together all the various proteins in our body. And we got tens of thousands of proteins that we make. Okay? And what are proteins made of? They are built from those amino acids. Okay? There are 20 different amino acids that we use, and what various chains we make of these amino acids make up our proteins. But going back to that functional group part, you remember we looked at those functional groups, we talked about that amine group, right, and that carboxyl group. So all amino acids in our proteins, they all have an amine group and they all have a carboxyl group. Okay, therefore the name of this molecule, amino and a carboxyl, because remember this hydrogen here can be released, amino acid. Okay, so all your amino acids, every single amino acids have this amino group and this carboxyl group. What differs between the amino acids is what carbon, hydrogen, oxygen, whatever atoms are put here. Okay, so let's look at valine. Valine has a amino and has a carboxyl. But then when you look at the R, the functional group for it, it is this here. Okay. Now you look at tyrosine, again, amino acid. We have an amino group and we have a carboxyl group, but instead of looking like this, we have this carbon ring for the functional group. Okay, so all your amino acids will have amino group and a carboxyl group. And we'll see, remember, if you remember, all our large molecules were done by dehydration or condensation reactions. So we'll take this H here with this, make our peptide bond. Alright, so we'll have these long chains of amines and carboxyls of the different amino acids bound together, and then we'll have these R groups projecting out from them. Okay, so the bonds are made between here. This would be bond. Okay, there would be another bond here and another R group here. Right? So these groups here are going to give the functionality of the proteins. Just as I said, we're going to be doing a dehydration or condensation reaction. See, we're making those bonds between there. We get these long chains made up with those amino and those carboxyl, and we get these what we call peptide bonds. Okay, the bond between the different amino acids is called peptide. Okay, and you can call these a polypeptide. Okay, but this is what these chains are what are going to form the amino acid. Okay, and we're going to look, there are different levels of structure of the protein, because this chain here, this long chain of amino acids is not a functional protein. This chain just gives it its primary structure. Okay, and what makes different proteins are what different R groups are made. So the codes for the DNA tells us which amino acid goes where, which one's first, which one's second, which one's third, and they can be all of different varying lengths and have all different kinds of amino acids here. Okay, but this chain of amino acid, this is the primary structure of the protein. So proteins, to be functional, they have the chain of amino acids, but then they get folded up in this three-dimensional type looking structure. And the first folds are going to be considered the secondary structure, and they're made up of parts of the protein will have alpha helix, and some have beta pleated sheets. So here's the alpha helix. You may have seen this, the alpha helix, when you look at DNA. Okay. But it is an interaction. You can see these hydrogen bonds, right? You've seen them as little dashes. These hydrogen bonding helps fold this protein, and some fold up in alpha helixes, some fold up in beta sheets, but this isn't secondary structure. Okay, this is the first part of the folding. Again, I'll repeat it. These proteins have to have this proper folding, or else they do not have functionality. Okay, so the hydrogen bonding between this carbonyl and the amine give us that secondary structure. Okay? In some proteins, part of the protein may have an alpha helix, part of it might be beta sheet. Okay, it just depends on the different proteins. All right, and now we get tertiary structure. Right, and tertiary structure is typically formed by the functional group, that R group. All right, remember these chains, they're made with peptide bonds, and we'll have, each amino acid, wherever it is, will have a R group coming out of it. Depending on what protein, what amino acids, okay, determines on what R group is sticking out. You can see here, this is the R group from amino acid in this part of the protein. This is R group from an amino acid in this part. But we're getting ionic bonding between this and this R group. Okay. Here's tyrosine. Right, here's another R group, and now we're getting hydrogen bonding between these two R groups. Okay. We did one of the bondings or forces. We didn't talk about van der Waals forces. This is, you can see, nonpolar. Attracting a nonpolar is a van der Waals force. But then we can also get covalent bonds between the R groups. This would be the strongest. Okay, sulfur, sulfur. Okay, so it's the interaction between the R groups give us a tertiary structure. And you can see how this is important, because this bending of the protein to give the protein its three-dimensional structure, give it its functionality. Okay, allows the protein to be functional. If this interaction right here is not taking place and this isn't bended, say this goes up like this instead of out this way, this protein may not be functional. Okay, so it is important that we get the correct amino acid in the correct position so we can have this proper interaction. And that's essentially what's happening in mutations. When you have genetic mutations, if you get the wrong amino acid here, you may not have this interaction and you may not have this fold, and therefore the protein may not be functional. And again, these proteins are involved in the functioning of the cell. They allow chemical reactions. Some of them are enzymes. Okay, they serve a function for the cell. And if this is a very important function, okay, your cells might not be viable or might not operate properly. So that's why these mutations sometimes lead to diseases. Okay, because you don't have the functional protein and you lose that function in the body. So let's look at what happens. You can see here is a normal protein. We have that strands of amino acids, but you can see we have some alpha helixes in the different portions, and then we have the tertiary structure. So here's the secondary, the alpha helixes, and then we get these further foldings to give the tertiary structure. So you can see this is highly three-dimensional. We got a three-dimensional structure. So this would give us our functional protein. Okay, proteins can be denatured. Okay, you can disrupt the bonds between the tertiary structures or between the R groups, and also disrupt the bonds of the alpha helixes. And if you do that, that is called denaturing. One way is high heat. High heat will unfold this protein. Also, pH, changes in pH. To get proper folding, these proteins need to have a proper pH. The pH can disrupt the bondings between those R groups or the hydrogen bonding. And if it happens, you get denatured protein, and now we just have a simple strand of amino acids here in the denatured protein. This protein is not functional. So the proteins can't function. An example of why this might be, doctors, they'd recommend pregnant women don't spend long stretches in hot tubs. So if you're pregnant, you shouldn't be sitting in there for 2-3 hours, because that'll bring your core body temperature up. Maybe up high enough to have high enough heat to denature some of the proteins, and many proteins are needed for development of the baby. So, although you probably wouldn't need extreme, but it's probably don't want to take any chances. So, but that's an example of heat may cause denaturing of the protein, and if the protein is denatured, then it is non-functional. And then there are some proteins that have a quaternary structure. Okay, so this is above tertiary. Not all proteins have this, because some proteins just operate solely alone, and they would just have tertiary structure. But some proteins, to be functional, they have multiple. Okay, this is one protein, this is one protein, this is one protein, this is one protein. And this molecule we'll be talking about, hemoglobin. This is the molecule that carries the oxygen in your blood. But for proper functionality, it has to be put together with 4 proteins, and then it gets more folding. It gets a quaternary structure to it. Okay, instead of just tertiary. Some proteins, though, operate solely by themselves, and so they would just have tertiary structure. Okay, but some do operate together, and they would have quaternary structure. So here's an overview of protein structure. Okay, we got the primary structure, and that just consists of the strand of amino acids that's put together with those peptide bonds between each amino acid. Okay. And then the secondary structure can consist of pleated beta sheets. Okay. We got the hydrogen bond interactions helping fold this primary structure, or it can also be alpha helix. Okay. Or a protein can actually have both secondary structures. And then we have the tertiary. That's the interaction between the R groups, okay, making more folding. And again, this protein has to be properly folded to have its functional use. And then ultimately, some proteins have quaternary structure. They are bound together with multiple proteins. Some exist simply as this in the tertiary structure, and they're just work individually. And besides the folding, there can also be structures or conjugates added to the protein. Proteins can have carbohydrates bound to them, okay, on the surfaces usually, or they can have lipids. Okay, and that's common lipid protein, you know, is cholesterol. Looking at the low density lipoproteins, these are all what we call the good and bad cholesterol, are made of lipoproteins. They're proteins bound with lipids. Okay. So we all know DNA is important. We've all heard it in the news. Even if you haven't taken biology, you're pretty well versed on DNA being important because it holds those genes. And again, those genes are just basically the code for making the proteins. Which amino acids needs to bind first, which needs to be bound second, third, fourth. So it gives the order of the binding of the different amino acids. And that's important because we need the proper sequence of amino acids so we can get that proper
folding, that secondary and tertiary structure to them. But like we said, these proteins are the functional molecules of the body. Okay? We serve many functions. We have some that are structural. You guys probably remember collagen, keratin from your integumentary days in anatomy. Ones we're going to be talking a lot about are enzymes, ones you've heard in the news lately, antibodies for the coronavirus. Okay, those are proteins that are made by the body. And then receptors, these are just some of the functions of, but we got roughly 19 to 20,000 genes, and we actually make upwards towards 100,000 different proteins and bind hormones. So we will be talking a lot about receptors. We'll get in antibodies a little bit when we get to immunity, our immune system, the lymphatics. But enzymes we're going to be talking a lot, because enzymes, if you remember, are used in catalyzing reactions. And we're going to be talking about chemical reactions quite prevalently. Now, the last of the large biological molecules we'll talk about is those nucleic acids. And the nucleic acids are basically the building blocks for the DNA. Okay, that's where we house our genetic information. That houses the codes for the different proteins we're going to build. Okay, and nucleic acids, the DNA, deoxyribose nucleic acid, and then there's also simply ribose nucleic acid, and that's RNA. Okay? But nucleotides, these are built. These chains, these long chains, okay, if you remember these strands, DNA is two-stranded, RNA is just one-stranded, but we have these long strands of DNA. Okay, we'll have these strands that are, this is 1 and this is 2, and they are put together. But how do we bind through here? How do we make the strands? Okay, that's going to be, the backbone is going to be the phosphate. Okay, so our nucleotides contain a phosphate group. They contain a ribose. Okay, in this case, for DNA, it's deoxyribose. For RNA, it is just ribose. Okay, and then they contain, for DNA, one of 4 different bases. And the bases are, there's pyrimidines, just a single ring of nitrogen, but that is cytosine and thymine, okay, for DNA. All right, for RNA, instead of thymine, we're going to have uracil. Okay. The other bases are guanine and adenine. Okay, so all DNA will have a phosphate and a deoxyribose, and then we'll have one of the varying nitrogen bases here. Okay, but the strands are made up of strings of phosphate bound to the deoxyribose, and we just continue making that strand down. Okay, and so the bases come out this direction. They make up the rung of the ladder. Okay, so this strand will have certain base, and then this strand will have bases sticking out. Okay, let's take a look at this. Okay, so here's how we're building. If you remember what kind of reactions, hopefully you're familiar with this now. We've already talked condensation, dehydration. Look at here, we're putting this base. Okay, that phosphate group's binding to the adjacent ribose, deoxyribose, and we're making producing water. And now we're making the strand. You can see the strand, that's the strand there. That is, okay, the rungs of the ladder are the latter here is phosphate and deoxyribose, and here is the base sticking out here. Here's the base making the rungs. All right, and you remember the other strand will have another base sticking out here and a strand of phosphates bound with deoxyribose, with the bases making up the rungs here of the ladder. Okay. And that gives us rungs. We'll see DNA is held together by, when we see these dashes, hydrogen bonding. So hydrogen bonding between the different bases. The base from one strand, hydrogen bonds with the base of another strand. Okay. Hydrogen bonding here. And those of you that haven't had much biology or haven't seen DNA, you will see that the bases that are here have a corresponding base on the other strand. So you will see the complementary base for guanine will always be hydrogen binded with cytosine. And then thymine, the complementary base is adenine. This is for DNA. For RNA, we will find it is uracil instead of thymine with A. Okay, but this is how it works. They will always complement and hydrogen bond with each other. Okay, so if you have, say, 50% of the strand is guanine, this strand, 50% of the strand should be cytosine. Okay, because these always are complementary with one another. Okay, and that gives us the code. What's besides, we've seen DNA. Here's the complementary, and this DNA binds in this double alpha helix. Okay, double alpha helix. You see our hydrogen bonding here. G with C, A with T. Okay, again with RNA, that would be a U. That would be a uracil. Okay. What's the difference? So the difference between RNA, ribonucleic acid, and deoxyribonucleic acid, DNA, is first the sugar that makes up that strand. Okay, ribose has OH. This is deoxy. We're missing an oxygen here compared to the ribose. Also, we've already talked about, so the base thymine, it will be uracil. Uracil will complementary strand with adenine with the A. And then the other is RNA is single-stranded, where DNA is double-stranded. So there, when you make a strand of RNA, there is no complementary strand with it. DNA, there are two strands. Some other RNAs, there are multiple types of RNA and serve different functions, is when we go to make our proteins, we don't make our proteins directly off of DNA. We actually just copy a part of the DNA, and that copy part is the messenger RNA. We copy the gene, the single gene from the DNA, and that copy is the messenger RNA, and it will contain the code for the amino acid addition for the proteins. Okay. There is another type of RNA, transfer RNA or tRNA. You'll see this written as a little mRNA and this one as a little tRNA. The tRNA, transfer RNA, is the one that will carry. So where proteins get made is at the ribosomes. We'll talk a bit later on when we talk ribosomes. Okay, the RNA gets made at this ribosome. This is the messenger RNA here. It contains the code. The tRNA brings in to the ribosome the actual amino acid that has to be put together. This tRNA will bring in what's there. All right, and so here is the amino acid it's bringing in. It will complement with the messenger RNA, and you can see we build. These are all red dots are amino acids. We're building our protein. Okay, and then another type of RNA is the RNA that makes up part of the ribosome. Ribosomes is these 2 units here, and this is where the protein is going to be put together. This is where the messenger RNA gets read, and the tRNA comes in to bring the proper amino acid. So besides just making up those codes, making those genes, nucleotides also serve other functions throughout the body. Okay, we're going to see a few. We'll be talking a lot about ATP because your body needs energy. It needs energy to perform these functions to make these cells viable. Instead of like your car uses gasoline, the energy that the cell is going to use is ATP, adenine triphosphate. So you can see we have 3 functional groups bound together. And just kind of pushing this forward is, remember these bonds. These are covalent bonds. These bonds have energy. Okay, if we break them, there can be a release of energy. This is a very high energy bond right here. When we break this bond, there is energy released, and that energy can then be used to do work in the body, do work in the cells. Okay, so we'll talk about this. We're going to talk a whole lecture on how this ATP gets formed when we talk about cellular respiration. Okay, also regulators of cellular events. We'll talk cyclic AMP quite a bit because it is involved in signaling in the cells. When we're making our ATP, we have a coenzyme, adenine dinucleotide, NAD, okay, for short. We will be talking about this when we talk about the cellular respiration that's being used to make ATP. Right? And then they can also be used as communicators, neurotransmitters between the cells. All right, so that finishes up with chemistry. Again, I'll make the caveat, if you're having trouble with this, I know this is kind of the stickler point, but we got to know this stuff to use it going forward. Okay, this is going to be in your physiology toolbox you're going to be using throughout the semester. Okay, so I need you guys to understand this, because if you understand this, you're going to be able to grasp it much better when we talk about this stuff, this chemistry stuff, in regards of how the different cells of the different organ systems work. So please, if you're having trouble, make sure to get a hold of me so we can discuss it in further to make sure you got a good grasp of this. All right, thank you.